Hello all, let's solve another Leetcode question. Problem for today is number of islands. I would suggest pausing the video and going through the entire question. So in this problem, we're given a grid with ones and zeros, ones representing land and zeros representing water. We need to find the total number of islands, and an island represents a group of ones connected either horizontally or vertically and surrounded by water. And we need to count the total number of such groups or islands. So in this example, we've got 4 rows and 4 columns and different ones and zeros. And if you have a look at how they're arranged, we can observe that all of these ones are connected together, and that can be one island. And we've got these 3 ones connected together. So the total count of the number of islands that we need to return would be 2. It's quite evident when we see a small grid like this, but we need to think of how this can be done programmatically or using some sort of algorithm. So as the first step, we can think of starting from the first one and discovering its neighbors which are connected either vertically or horizontally. So let's say we started with this one, we would maybe come across these 2 ones. In turn, each of these might have neighbors. And in this way, we could cover all the ones that are connected together. This strategy or method can be used in a lot of problems, especially in trees and graphs. And I like to call this the explore method. We're starting at a certain point, and based on our condition or what we're searching for or looking for, we explore all the connected components. And in graphs and trees, there are 2 important concepts which help us do this exploration. They're called DFS and BFS. DFS stands for depth first search, and BFS stands for breadth first search. They basically work the same way. Let's say we started with a certain one. We would want to explore all the different directions or connections for this node. So we can go top, right, bottom, and left. In this way, we explore all the neighbors or connections till we achieve what we want. So for this particular example, let's say we started with this one, we would explore different directions. So we go top, there's nothing here, so we go right. And then we found a 1. So in depth first search, we go along the entire depth before exploring the next direction. So when we come across this one, there's again nothing on top, so we explore this one. So we've come to 1. So from the first node to this node, there's a certain depth where we've come across 2 ones. Then there's nothing surrounding this one, so we go back to the previous one and explore this one. Then we go back to the first one and then explore this one. So in this way, we've covered all the ones that form an island and increment our count to 1. Similarly, we can go across the other elements, which are zeros. So we iterate over all the others, and we see that it's 0, so nothing to evaluate here. Then we come across this one and do a similar process or exploration around this node. And that would cover all of these, and we increment our count to 2. Then we have a couple of zeros that we again go through. Then we can return our result. So whether it's depth first search or breadth first search, the core concept remains the same. The difference being in breadth first search, we start with a certain node and evaluate its neighbors before going further. So in this case, let's say we started with the first node 1, we would first take these 2, which are neighbors. And then when in turn we're evaluating, for example, this node, we see its neighbors. So in this way, we're first evaluating breadth-wise and arriving at the result. And either approach can be used, but on initial observation, you can see that in the worst case, with the grid being all ones, in depth first search, we would have to go through the entire grid and add them to the stack, which is considerably more space complexity than breadth first search, where we just have the neighbors in the queue at a certain point. We will go into the time complexity later and discuss about it with different examples, but let's proceed with implementing this solution using breadth first search. So for breadth first search, we take a certain node, evaluate all of its neighbors, and then proceed to the next one. So let's see how our pseudocode can look like on a high level. So we need to traverse the entire grid. So we can just do for I in R, which is all the rows, and then for j in C, which is columns. So in this way we traverse, and then for each element we see if it's a 1. So if and let's say the input is grid, which is a 2D array. So we want to check if grid of I and j is equal to 1. So in this case it is a part of an island, so we can increment our count. Initially count can be 0, and then we can do a BFS on the grid starting at that point. And let's see how our BFS helper method looks like. We want to maintain a queue which can initially just have the first element, which is I, j. And then we want to keep iterating till the queue has any elements. Then we explore each direction. And then add to queue if 1. So this kind of explains it on a high level. There's a lot more to do when we actually code it out. Let's jump to Leetcode and try implementing the solution. As a first step, we can just check if not grid. Return 0. Initialize a count, which will be 0, and we want the number of rows and columns, which will be quite handy. So let's put that in R and C, and the number of columns will just be the length of each row. Now we traverse over the entire grid. We're only concerned if that particular cell is a 1. If it's a 0, we can just ignore it. So we check if it's equal to 1. In this case, it means it's part of a certain island. So we increment count. Now we want to update all the ones that are part of this island. And this is done by doing BFS. And while doing BFS, whenever we encounter a 1, we can make it a 0, which means that it's already accounted for. So let's use a helper function here called BFS. And we pass in ij. Let's implement the helper function. Let's call it row and column here so that it's not confusing. And because we are seeing this row, this particular cell, we can make that a 0, so that next time we encounter it, we know that it's already been explored. We can use a queue here for doing the popping and maintaining the neighbors which we want to explore. And from the collections package, there's dequeue, and initialize it with this particular cell. Now we want to iterate as long as there's elements in the queue. We could write multiple if conditions like 0 less than or equal to row plus 1 less than r, less than length of grid. We actually might need the row and column lengths quite often, so let's put that here as well. And so in this case, we're keeping the row same and increasing the column by, we're incrementing the row by 1 and keeping the column same, which means it's the element that's below the element we're looking at. And writing a lot of these conditions can become a little messy. So as an alternative, let's just list out all the directions and then loop over it. So we can have directions equal to 0, 1, 1, 0, which means down, 0, -1, which is left, and -1, 0. So if you look at these directions, that's the value by which the row number and column number are changing for each direction. So in this order, it's right, down, left, and top. So we can, instead of this, let's do for D in directions. And we want ij for the element we're looking at. So let's pop it from the queue. And we want to see the next one that we're looking at. So let's call them next I and next j. It would be the particular row number plus the direction that we're seeing over here. So it'd be I plus D of 0, and the column would change by D of 1, so J plus D of 1. The same condition that we discussed earlier, so it'll be and we want to check if it's equal to 1. So if it's a 1 and it's one of these neighbors, it belongs to the same island. So let's first append it to the queue. So that it's explored again for any connected neighbors. And since we've already seen this, we can make it a 0. So when we do this entire BFS, we're exploring all the connected neighbors and making them zeros because they're part of the same island. And we also incremented our count, so at the end of this, let's just return the final count. Let's run this code to see if it works for the given example. Yes, it does. Now let's submit the solution to see if it works for all possible inputs. Yes, it does. Let's go back to the solution and see how we actually implemented it. So we're going through the grid, and as soon as we encounter a 1, we're doing a BFS, updating all the ones around it as zeros because it's part of the same island, so that next time when we're traversing and come across a certain element, if it's a 0, it's already been taken care of. And this is the core concept, and this BFS could easily be replaced by a depth first search as well. But one thing to observe is that we're actually updating the grid that we get as an input, which you might think as changing or modifying the input data. So this can easily be avoided by either cloning the grid to a new one, or also using like a visited array, a visited set, which can store all the elements that were already visited. That's another option. Or one more thing we could do is, we know that the final grid would always be zeros and ones. So instead of, when we see a certain element, instead of making it a 0, we could make it a 2. That way we go through the entire grid, and in the end we'll have zeros and 2s. So we traverse it again and make all the 2s 1s again. That is not changing the time complexity, and is a good trick or a good approach to do it in place without using extra space for the grid itself. I hope you get a good idea of the solution now. And let's jump back to discussing about the space and time complexity. For this example, we have a grid with M4 and N10, and we're doing BFS or breadth first search. So firstly, the time complexity. We are traversing the entire grid, which in itself would be big O of M cross N. And additionally, when we encounter a certain element, we're seeing all the neighbors, which are part of the same island. So we might encounter the same cell a couple of times, but even then, it's not increasing as a function of how many times we encounter, right? It's just maybe a small multiple or something added to that. So the time complexity would simply be big O of m cross n. Secondly, space complexity, which can be a bit tricky. In this case, we're using the grid itself to indicate whether a certain element is being explored or not by making them zeros. So we're modifying it in place. And the additional space we're using it is for the actual queue when doing BFS. So let's see how that works. We start from the leftmost element, we add this to the queue. And next, we pop this element and add both of its neighbors, which would be this entire set of ones here. And after that, we pop this one, add these two ones, we pop this one and add this one. So now we've got all of these in the queue. Next, we pop this one, add these two, pop this, add this, pop this, add this. So we've got all of these. And going forward, we pop this one, add these two. So in this case, how many elements do we have in the queue? It's mostly all of these elements plus a couple of elements from the next diagonal or the cross set of ones that we're seeing. So it's always, if you see here, it's always 4 plus something, right? And this something is not actually increasing based on n or based on the number of columns we have. So this was 4 cross 10, but let's say you had 100 columns here. Would this time complexity or the size of the queue change according to 100? No, in this case, it's just changing according to m itself, which is 4. So the space complexity is actually increasing as a function of the minimum of m comma n, in this case, the minimum of 4 and 10, which is 4. So the space complexity can be written as big O of min of m comma n. And another example for this was, let's say we swapped it around where we had a vertical grid where m is 10 and n is 4. So it would look something like this, where we had 10 rows and 4 columns. So even in this case, when we start exploring, we're actually exploring like this, where we're always limited by one of these boundaries, either the number of rows or the number of columns. And the minimum of those is actually the function by which the space or size of the queue is increasing. So thus, big O of minimum of m comma n is a good approximation for the space complexity. Hope this helped. Thank you.